All right, let's talk about something that sounds like it's straight out of a sci-fi movie but is getting more real by the day, quantum computing. We're going to treat this like a mountain climb, breaking down this huge concept step by step to see the incredible new reality that's waiting for us at the top. So here's our route for the climb. We'll start at the very beginning with the basic building block. Check out the wild and powerful tools it lets us build, and then we'll face the real-world storms at the summit and the clever ways we're learning to navigate them. First things first, we're at base camp. Before we get into what makes these machines so incredibly powerful, we have to get our heads around their most basic fundamental part. You know, the entire promise of quantum computing, all of it, really boils down to this one kind of weird, mind-bending question. What if the basic language of all computers, that little bit, wasn't just a simple on or off switch? Well, the answer to that question is the qubit. Think about it like this. A regular computer bit is like a light switch. It's either on or it's off. A qubit, it's more like a spinning coin. While it's flipping through the air, it's not really heads and it's not really tails. It's kind of both at the same time. This ability to be in multiple states at once is called superposition, and it is the first quantum superpower. So how do you even picture this? Well, scientists use something called the Bloch sphere. If a classic bit can only be at the North Pole for a 1 or the South Pole for a 0, a qubit can be anywhere on the surface of the entire globe. Every single point on that sphere is a unique state, a different mix of 0 and 1. This just opens up a massive, infinitely richer world for computation. Okay, so we've got our fundamental building block down. Now, let's start our ascent up the mountain. What can we actually build with these incredibly powerful qubits? Welcome to the Quantum Algorithm Zoo. Now, don't worry about the complicated names here. What's important is that each of these is like a unique, special key designed to unlock a very specific type of problem. Shor's algorithm, for example, is famous because it could potentially break most modern encryption. They're all like special recipes that use quantum weirdness to get answers at speeds that are just impossible for any regular computer. And let's be really clear about this. We're not talking about a small speed boost, like 10% or even doubling the speed. For the right kind of problem, this is an exponential leap. We're talking about the difference between a calculation taking a few minutes versus it taking longer than the age of the universe. It's a total game changer. All right, let's zoom in on one of these. To really get a feel for this quantum advantage, we're heading for the summit by looking at one of the most famous algorithms of them all, Grover's search algorithm. Now, the problem Grover's algorithm solves is actually pretty easy to understand. Imagine you have a gigantic phone book with a billion names, but they're all completely jumbled up, totally random. Your job is to find one specific person. How would you even begin? And this is where the magic happens. A classical computer has no choice but to go through them one by one. If you have a trillion items, that's on average 500 billion checks. But a quantum computer running Grover's algorithm can use superposition to check a whole bunch of possibilities at once. It only needs about the square root of n, so for a trillion items, that's roughly 1 million checks, from 500 billion down to 1 million. That's not just a party trick. This kind of power could totally revolutionize things like drug discovery or solving massive logistics problems. Okay, so we've reached the summit, and the view is absolutely incredible, but a storm is rolling in. Now we have to talk about the single biggest challenge that's holding quantum computing back from changing the world today. We are currently living in what scientists call the NISQ era. Our quantum computers are incredibly powerful, but they're also unbelievably delicate. Think of them as the most sensitive microphones ever built, trying to record a tiny whisper during a rock concert. The slightest vibration, the tiniest change in temperature, that's noise, and it can completely wreck the whole calculation. This quote from one of our sources just hits the nail on the head. You can run a totally flawless quantum calculation, but the entire thing can fall apart at the very last second, just in the simple act of trying to read the answer. And this brings us to this critical problem called readout error. It's basically like static on a phone line. The qubit is holding the correct answer, say a 1, but all that environmental noise corrupts the signal, and your measurement device accidentally reads it as a 0. All that amazing quantum work, just gone, lost in the noise at the very end. But the storm doesn't mean our climb was for nothing. Now we get to look out at the horizon, where some of the smartest people on Earth are building the tools we need to calm this storm. This is a fantastic real-world example. It's a software toolkit called Qiskit. And you can see right there it has an entire component whose only job is to fight back against this noise. So this isn't some far-off theoretical problem. It's an engineering challenge, and people are building active solutions for it right now.
So the strategy right now isn't to build a perfectly silent, flawless computer. That's probably still a long way off. Instead, the big focus is on error mitigation. This involves a bunch of really clever software tricks to measure the background noise, figure out how it's affecting the results, and then basically subtract that distortion from the final answer. It's how we pull a clear signal out of the noisy machines we have today.
And that pretty much leaves us here, looking towards the future. The race to build a useful quantum computer isn't just a numbers game of cramming more and more qubits onto a chip. The real challenge, the true finish line, is making those qubits speak clearly. The big question isn't just how big can we build them, but how well will we be able to listen?